But without further ado, thank you all so much for coming. The first talk we have today in this room, of the 6 that we'll have here, is Go Security, Past, Present and Future, from a former member of the Let's Encrypt project, and now heading up the Go Security team at Google. Please give an absolutely massive hand for Roland Shoemaker.
Thank you. All right, so thank you for the introduction. Like you said, I'm Roland Shoemaker. I run the security team at Google for Go. And we're going to kind of go over why you probably haven't heard of what we do and why that's probably a good thing. So first, we can give a quick overview of what the team actually is. The Go security team started sometime around the beginning of 2020, formally. I don't think any of us actually know the exact date. And it's existed in basically the same form since then, with various numbers of engineers. Currently, we have 5 people who basically work full-time on the security of the language. So me and a handful of other people. And the reason the team was started is that Go has become a very important language, not just for Google. Kind of across the industry, people are using Go to build massive services. And if something in Go breaks that can cause a security incident, that's really bad. Not just for Google. It makes us look terrible, but also, we don't want people losing information, basically having security breaches. So the main way that people probably interact with us is through this email address, security@golang.org. And this is where we get security reports. So most of the issues that are discovered in Go are not actually discovered by us. We go over the language with a fine-tooth comb, but we don't find most of the issues. Typically, it is either external security researchers who, this is their job. They look for security issues. And they will send us an email and say, hey, here is something that is wrong with Go. It is either crashing with unexpected input, or something you have said works one way actually works another. And technically, there is also another way people can contact us, which is through the Google Open Source Vulnerability Rewards program. And most people don't actually know this. So if you have ever sent an email to this, which unlikely, but if you have, you can actually also submit this through a Google program that will give you money. We try to, when people send us a lot of emails, we tend to say, hey, you should go and do this other way, because they will pay you. And we technically can't do that. So the other thing that we do is we own what we consider to be the security critical packages in the Go standard library. So the most obvious of these is everything in the crypto tree. Every crypto algorithm, for encryption, password hashing, regular hashing, protocols like TLS or X509, things like that. We also own what we consider to be the critical production stack for Go. So the things you need to write a network service. Net HTTP is a good example of this. Things you might not think of are things like encoding JSON. Probably 99% of the usage of encoding JSON is to take something off the wire and decode it. And that can be incredibly security critical. If there is something broken in this package, it turns out that huge numbers of network services would be broken in horrible ways. And then there's a whole bunch of other stuff. Anything that passes untrusted user input typically is considered security critical. So, image parsing libraries, which are the bane of my existence. Archive packages, the zip package, the tar package, things like that. And then we also own everything else that could have a security impact on Go. So the module, the security aspects of the module proxy, the sum database, and then there's a whole bunch of other stuff that is kind of internal to Google, the security of the Go team at large, which I won't really talk about because it will be of interest to absolutely nobody. So first, let's talk a bit about Go's security history. Go is, because it is a memory-safe language, we don't have all of the classic security bugs that you will get in C. We don't have memory corruption. technically, there are some places we have memory corruption. But for most of Go, that's completely uninteresting. So I tried to, I looked up some CVE data. If you don't know, CVE is the Common Vulnerability Enumeration. I forget exactly what it stands for, but these are vulnerability reports that the industry have used for about 30 years at this point. And I'd looked at, what other languages that you could plausibly compare to Go and what numbers of CVEs they have. Now, you will notice that we are not the best of all of the languages here. Rust is significantly better. But really, one of the reasons that Go has this many CVEs is because Go comes with this massive standard library. So any security issue in any of the, I don't know what it is, 60 plus packages that we have in the standard library, we have CVEs for. Only 20 of that 160 CVEs that we have ever had for Go are actually in the tool chain itself. So these are things that affect your usage of the Go command. And these are kind of often some of the highest impact vulnerabilities. And only 20, I think this is, very impressive. I mean, comparing to Python and Node.js is perhaps a little unfair, but we have done pretty well. One thing I really do like to brag about, though, is that Go's crypto libraries, it's very hard to compare to other languages because almost every other language ends up having wrappers around OpenSSL. OpenSSL is the only other project that probably has the same breadth of cryptographic implementations that Go has. And this is slightly unfair because OpenSSL is written in C. So maybe not 90%, but a very high proportion of the CVEs in OpenSSL are from memory corruption. Of course, the rest of them are because OpenSSL has been around since the 90s. It has implemented every single possible optional cryptographic algorithm or extension to a cryptographic algorithm, an idea that somebody had and they wrote down on a napkin, they implement it. So when you do that, when you create this huge, vast swath of options, you run into the problem that a lot of them are not, the interaction between lots of things are not well thought out. So one of the things that we did when we developed our cryptographic packages is we are very selective about what we actually implement. We mostly only implement things we actually think are going to be useful to people. And, very niche algorithm, there's a whole series of encryption algorithms that we just have no interest in implementing. People come to us every so often and say, hey, could you please implement this? And unless there is, a popular protocol or a really strong reason to implement it, we basically say no. And that, some people have gotten very angry at us because of that. But I think these numbers show that we have probably made the right decision there. And we did an analysis of all of the CVEs that affected the cryptography packages about a year or two ago. And we kind of tried to, the Go project doesn't assign severities to vulnerabilities. Oh. I probably should have turned off the sleep on my laptop. So we went through and we tried to say, if we were to assign severities, what would we have assigned these 40 vulnerabilities? And we decided that only 4 of them were actually considered high impact. And high impact means that this being broken could fundamentally impact the security of an application that is built on top of this. So this is things like incorrect results from cryptographic algorithms, signatures not being produced correctly or verified correctly, oracles in encryption and decryption, stuff like that. And this is compared to the OpenSSL 80 high impact. I think this is, if I get to brag about anything, I think it's this. So because Go doesn't have memory corruption vulnerabilities, we tend to see vulnerabilities fall into two very broad categories, I must say. The first is denial of service. This is, you can cause a program to panic or to use more resources than it really should. So consume large amounts of memory, consume large amounts of CPU, things like that. We tend to consider these to be quite low impact to the Go ecosystem. Go is very often used to build network services. And the infrastructure around network services these days is often very resilient to programs just crashing. So, it's not great. If someone can just send a request to your HTTP server and it crashes, that's not good, but it's also not the end of the world. Usually most services will know how to recover from that. And then the other, which is an unbelievably broad bucket, incorrect behavior. So these are typically what we would consider logic bugs. We implemented something incorrectly. We've documented an API to do one thing and it actually does another. And these tend to be significantly more serious. Logic bugs can really break your program. The classic example is if you are trying to verify a hash or a password or something, if we say this is, these two hashes match when they don't actually match, that's just breaks every Go security guarantee that there is. So I'm going to talk a little bit about the different type. First I'm going to talk about denial of service, right? So denial of service for Go typically falls into two different categories. One being you cause a program to panic. There's two ways you typically do that. One is that you trust the classic example is in a parser. You trust the input data to say to actually describe the data that your program is ingesting. And then you do a slice operation. And you say, I want to access this portion of a byte slice. And of course, you haven't checked that that the header from whatever this data is accurately reflects how much data is in the byte slice. And all of a sudden, you're trying to read outside of the end of the slice. In C, this would be very serious. Of course, in Go, your program just panics, which is not good, but it's not terrible. And then the other example of this is nil pointer dereferences, which happens less often in terms of security context. It's usually just a programming error. And then the other is allowing untrusted data to make allocation decisions. So in this case, in the second case, you pass some header from a data and then use that untrusted data as an input to make or allocate some kind of slice or other object. And we actually see this incredibly often. You will have this headed items will be 10 million, and your program tries to say, okay, I will allocate a slice of integers 10 million long. All of a sudden, your program grinds to a halt because all of the memory has been consumed. And that can either cause your program to crash, or if somebody is being very smart, they choose a length which is not too high, not too low, and then they can just slowly consume huge amounts of memory on your system. So incorrect behavior is much more interesting to me. And most of the time we get, in the Go language in particular, we get logic bugs is because we are implementing something that is either very confusing or very vague. So you read a specification and you say, yes, I have implemented all of the things the specification says. But the specification leaves out about 80% of the security considerations about implementing this protocol. And because of that, you introduce all of these security bugs. And the prime example of this is something like implementing HTTP 1.1, which is a great specification for its time, but made absolutely no considerations for security. So there's a whole bunch of things around, how many headers is it reasonable to pass from an HTTP request? Or, how long of a body of an HTTP request should you be happy to read? Of course, the specification makes absolutely no comment on this at all. This when the HTTP specification was written, it predates when the IETF required that you have what is referred to as a security considerations section, which says, you really need to think about these things when implementing this protocol. And then, another example is the HTML. We have an HTML parser in the XNet package. And similarly, the HTML specification has gotten a lot better since it was adopted by the WAT working group. But the original HTML parsing specification is absolutely horrendous. Even the current one has kind of infinite loops where it tells you how to walk through the DOM, and you get halfway through into this weird state, and then it says, go back here, and then you end up in an infinite loop. And if you know how to write parsers, you just implement some kind of maximum depth limit for your parser, and you say, OK, I'm just going to stop here. I'm not going to stop trying. But of course, the specification makes absolutely no comment on doing this, which is unfortunate. And then the other thing that we see often is misalignment of implementations. So what I mean by this is when we have an implementation in Go, and then there's an implementation in another language. And because of the vagaries of a specification, or sometimes we just implement the specification wrong, our implementation will result in a different result than a different implementation when given the same data. And this is, it's arguable, the security impact of this. It's often very dependent on where it is that this problem arises. But we see this often in things like HTTP, where if you're implementing a proxy in Go, and we read a request one way, but your downstream HTTP server reads it another way, it gives an opportunity to kind of sneak data through in a way that can be quite dangerous. So the other thing we see is low-level APIs are really a bad idea. Giving access to people to really dangerous primitives can allow people to do really interesting stuff. But often you really need to think hard about how you use those primitives. So we have one example of this here, which is when we implemented ECDSA in the crypto tree. In order to do ECDSA, you have to do a lot of mathematical operations over elliptic curves. And we had to write a package that did elliptic curve math, and we decided, let's make that package public. And it turns out that doing elliptic curve math is actually really complicated, and there's a lot of ways to do it really badly. And when you do it badly, it causes really bad problems, because all of a sudden, you get points on the curve that make you think that you have done the right thing, and in fact, you have taken a signature that is for the completely wrong thing, and all of a sudden it verifies for something else. And really, it turned out when we found this particular bug in the ECDSA package, we had done the right thing. We had checked that scalars were properly reduced. But in the elliptic curve package, we didn't make that check. We just assumed you did this. So anyone who was using this and didn't implement those checks themselves had a really severe problem. I don't think we ever actually found anyone who was doing that. But the fact that you had to know to do this is kind of an indicator that it was just not a safe API to produce. We could have added the checks ourselves, but we also should have just never made this accessible. And then I didn't actually put a slide for this, but the other thing here is assembly calls. For almost all of the really high, the cryptographic algorithms that people actually rely on, we have assembly implementations, per architecture assembly implementations. Because cryptography can be quite slow. And really, to kind of squeeze out all of the performance needed, you really have to do it in assembly, unfortunately. And those cores are kind of, I said parsers are the bane of my existence. Probably assembly is the bane of my existence. Because it's hard to review. You really, the Go assembly, or the Go assembler makes it slightly more complicated because we use our own bespoke instruction set that maps to per architecture instruction sets. And reviewing it is very complicated. You have to really know what the mapping is between the Go assembler and whatever architecture's assembly you're using. Spotting bugs is, very hard. It's very hard to test properly because you can't really do the same kind of coverage that you use for Go code for assembly instructions. So it's very hard to tell, am I actually exercising all the branches of this? Or if it's constant time code, am I actually exercising all of the non-branches of this code? And then the other thing is CGO. CGO is awful. If you really need to call into C, sure. But the problem is that as soon as you touch C, you get all of the memory issues that C comes with. And when I said there are 20 different security vulnerabilities in the Go toolchain, 13 of those are related to the CGO implementation. In fact, most of them are not actually CGO in the Go language itself. It's C flags and LD flags. If you've ever written CGO, you will know that we have special directives that you can put into your C that say, these are the flags to pass to the compiler, these are the flags to pass to the linker. It turns out compilers and linkers for C have this whole breadth of things they can do, like loading arbitrary modules that override parts of how the linker and the compiler work. So most of these vulnerabilities are related to the fact that you can pass a C flag that says, load this module, you run go build, and all of a sudden you have remote code execution. It's just executing whatever's in the shared object that you passed in. So we have an allow list for these, but it turns out that enumerating all of the safe flags is also incredibly difficult. We've made a number of mistakes here, and I'm sure there will be more in the future. So let's talk a little bit about what we're doing now. The first thing is, let's try and deprecate all of the mistakes that we made in the past. So we have a huge number of libraries. Some of them were written a very long time ago, before there was we made the same, we didn't make as good choices in the past. So there are a whole bunch of APIs in very sensitive packages that they're there. You really shouldn't use them. Because of the compatibility guarantee, we kind of have to leave them there. But we've been trying to deprecate them, add big warnings that say, hey, unless you really know what you're doing, please do not use this. I mean, the prime example of this is we have a function in the crypto RSA package that lets you decrypt PKCS1 v15 session keys. This is a really dangerous API. It's intended to let you kind of switch out a real key for a fake key in a constant time way so that, you can kind of transparently use either the right or a completely randomly generated key when you're decrypting a session. It's only safe to use really in TLS. And we use it in the standard library in the TLS package, but nobody else should really ever touch it. Because unless you really know how to design a protocol, you're probably going to get it wrong. And we have seen people get it wrong. So the corollary to that is adding safer APIs. When we design APIs these days, kind of the first thing we think about is, how could you misuse this? Is it possible to hold this in the wrong way and all of a sudden the security guarantees that we're trying to provide you just disappear? It's entirely possible we will still make mistakes. It's unfortunate, API design is a hard problem. So, we're trying, but don't hold me to getting everything right. And then another big thing is FIPS. Hopefully nobody in this room knows what FIPS is. If you do, I am very sorry. FIPS is a US government regulatory framework that you essentially are required to comply with if you want to sell software to the US government. In 2016, we added support to Go for FIPS. Now, we added this basically just for Google. Google is required internally to use FIPS cryptography, so all Go had to use FIPS internally at Google. But because Go is an open source project, we added the integration to the open source toolchain with a very big warning that said, if you don't work at Google, you really shouldn't use this. It is not designed for you. It is designed for us to use. And it turns out, despite the fact that you want people not to use it, a lot of people use it. And a lot of people have based a lot of their business model on using it. So every so often, we would get questions from people saying, can you add support for this? Here, I found this bug. Can you fix it? And we would have to say, did you not read the warning? We said we wouldn't help you with this. But nevertheless, they persisted. So in collaboration with Filippo, who is sitting here, we have, in Go 124, we have added support for a pure Go FIPS implementation. The previous FIPS implementation I didn't say, but is based on boring crypto. which is a C fork of OpenSSL that is used at Google. And because of that, all of the issues that I have with CGO are also present in this very important cryptographic compliance framework that we use. So in 124, we completely, Go's crypto libraries have everything needed to build a FIPS module. So we said, OK, why don't we just use Go? Why do we use C for this? So we, in collaboration with Filippo's company, Geomis, we developed a pure Go FIPS module, which is currently going through verification at NIST. If you know what that means, again, I'm sorry. At some point in the future, when the US government deems that we have done all of the things that you are required to be rubber stamped as a FIPS certified module, you will be able to use the pure Go version. And this is a completely drop-in. All you have to do is set an environment variable when you build your binary. It's great. It's significantly better than what we had before. And the other thing we did, I'll go through this very quickly. At the beginning of this year, we look at all of our crypto libraries. We tend to know what's in them. But what comes with that is kind of blindness. We look at it so much, we don't always see the problems that are actually there. So at the beginning of this year, we engaged an external company, Trail of Bits, to do an audit of all of our crypto libraries and to see, could they find anything that we had missed? And it turns out yes, but not very much. I think there was a total of 4, maybe 5 findings, of which only 1 we considered actually serious. The rest were all kind of internal implementation details that don't really matter. So it turns out we are actually quite good at writing crypto code. So the future, what are we going to do next? Testing. Turns out that there are 2 time-honored ways to prevent bugs from appearing in your code. The first is never write it. The second is really test it. So we have been kind of focusing on, finding test suites that we can apply to Go code across a whole bunch of, TLS, X509, all of these important protocols, even for some of the lower level crypto stuff. And then also trying to test, we're still working on this a little bit, all of our assembly implementations. So making sure that our constant time assembly is actually constant time, quite important. And then also testing that we actually test all of the non-branches in constant time code. The other thing is improving the security of the Go module ecosystem. There hasn't been a major impactful attack on the Go module ecosystem yet. It's kind of a matter of time until somebody tries to and probably succeeds in attacking the Go module ecosystem. So we have been looking into what can we do, especially at the module proxy layer, to make those attacks harder. I don't have anything public to share about this yet, but we have a whole bunch of kind of nascent projects internally at the moment that are focused on this. The next thing is post-quantum crypto. Again, if you actually know what this is, I'm sorry. At some point, quantum computer, depending on who you ask, at some point, quantum computers are going to render all of the cryptography we currently use completely useless. So we are looking to what the future holds in terms of implementing new algorithms. We have been a bit hesitant to just, there's a whole field of different implementations that we could pick to do this. We've been a bit hesitant to add these to the standard library yet. We're really trying to wait until protocols actually adopt these before we add them to the standard library. Because it's really hard, if you don't use crypto libraries in the standard library, it's really hard to tell what a good API looks like. We really want to actually have to use it before we can say, here's how you can safely use these APIs. The other thing is bringing govulncheck to the Go command. If you don't know, govulncheck is a tool we wrote to find public vulnerabilities in your source code. So this is currently in the golang.org xvuln repository. And it's just a binary. You run it over your source code, and it consults a vulnerability database that we host and says, hey, look, here is a call site in your program that calls a vulnerable symbol. You might want to look at this and consider how this impacts your project. And it's really good, but not enough people use it because it's not in the Go command yet. So we're hoping to bring it to the Go command. So how can you help us? If you are a security researcher, send me an email if you find something. If you run a production system and you notice weird behavior, we recently had a vulnerability reported to us about a race in the database SQL package because a big company was seeing weird results come back from their SQL queries. And it turned out that was actually a very serious security bug. And if you want to get paid, use the Google Vulnerability Rewards program. If you know about security footguns, if you have written Go code that has caused you a problem that may not necessarily be a problem in Go itself, let us know. If there are better APIs we can implement, we would love to implement them. We would love to make it easier, safer to use Go. And of course, keep using it. And with that, I think I perfectly hit my time.